Okay, welcome to the video lecture. Here we're going to start talking about LU and QR factorization, basically algebraic methods for linear algebra, for matrix algebra. And you can see here, I've described it, Unit 4, as fancy algebraic operations to subdue matrices into doing our bidding. So we're going to learn some more advanced matrix decompositions and ways to manipulate matrices. This is different from what we'll be doing afterwards, which is the next unit after this is iterative methods for linear algebra. So that's all about basically solving systems of algebraic equations through iteration. Okay, we'll start by talking about LU decomposition or LU factorization. And it's based on Gaussian elimination. So just to remind you what Gaussian elimination is, it's what you would use to solve a system like AX equals B using row operations. Now you might have done something like this, 1, 2, I'm just writing A here, 4, 5, 6, whatever, and then you would put the elements of B on the other side. And then you do row operations to make this upper triangular. And as you're doing those, you're changing these B things as well. So we're essentially going to do that, but we're going to treat it differently, focusing on the operations we do to A, and we'll record the operations that we would have done to B. And so thereby accomplish the same thing, but in a slightly more sophisticated way. Right, so let's start out with, let's start out with row operations on A. So how would you go about reducing A to an upper triangular form? So we would, first I'll number these rows 1, 2, and 3. And then what we'll do is we'll create a new version of the matrix, A primed. I'm just going to copy row 1, 1, 2, 3. Now row 2, I'm going to replace row 2 with a linear combination of row 1 and row 2. In particular, I'm going to treat this 1, that's my pivot element, and I need to subtract from row 2 enough row 1s so that I get a 0 where that 4 is. So I want to get a 0 here. So it'll be 4, right? The multiplier, which I'll call M21, is going to be 4 over 1. It's because the multiplier that I apply to row 1 is I divide by this pivot element and then I multiply by the thing I'm trying to eliminate. Now we'll get a 0 there. Okay, so I get a 0 there, and just to move things along, I happen to know these numbers. So this is replacing row 2, I'm getting row 2 prime now, is the old row 2 minus M21 times row 1. Next row, row 3, the multiplier, M31, is 7 divided by 1. So I'm going to replace row 3 with the old row 3 minus M31 times row 1. And I get a negative 6 here and a negative 20 here. Okay, so I've successfully done the first phase of Gaussian elimination and gotten zeros in this first subdiagonal column. Now I move on to the next subdiagonal column. So let's call it A double primed. So I copy my row 1, 2, 3, and I copy my second row 2 now because it's already done. But row 3, I need to replace with a linear combination of row 3 and row 2. And the multiplier I'm going to use is, just like I did before, negative 3 is my pivot element, and so I need to divide row 2 by that and multiply it by this negative 6. So my M32, so it's the third row, the second phase of Gaussian elimination, is negative 6 over negative 3. So I'm going to replace row 3 with row 3 double primed minus M32 times row 2 primed. And I get a 0, 0, and a negative 8. You can just trust me on that, or I encourage you to do the math anyway. So this A double primed is upper triangular. Upper triangular. In other words, it's got stuff on the diagonal, it's got stuff above the diagonal, but below the diagonal is all zeros. So everything on the diagonal and above is non-zero. And we often call that U for upper triangular. Okay. So LU decomposition or LU factorization is a way of decomposing a matrix into two factors, one of which is upper triangular like this, and the other part is lower triangular. So we've already seen how we get the upper triangular part. Now that you might be asking yourself, where does the lower triangular part come from? So what we're really going for is representing a matrix A and decomposing it to an L times a U, a lower times an upper. So we have this U part, so where does the L come from? So let me just tell you, and then I'll prove to you that this thing that I'm going to describe is in fact the L matrix, the lower triangular matrix. Okay, Gaussian transformation matrix. When you're doing Gaussian elimination, you're doing these row operations. Those row operations can be recorded in a matrix, and so that you could accomplish those row operations basically just by multiplying by that matrix. So that's what this matrix L is. So I'm going to write this big giant matrix. L sub k is this big thing here. Now this L, it's a diagonal matrix, so let me, sorry, it's like it's the identity matrix. It's 1 on the diagonals, on the diagonal. And everything else is 0 except for the row, sorry, the column below the diagonal in the kth column. So here's the kth column. Kth column. So this element, this 1 here, is element kk. So what we're going to do is below that diagonal element, we're going to record these multipliers that we were using in our row operations. So it's basically, let me zoom in on this, m k plus 1 k. So it's the multiplier that we use to operate on row k plus 1 at the kth step of Gaussian elimination. And then the next one is m k plus 2 row, column k, and all the way down to the bottom one, m n. So this is an n by n matrix. K. So this down here is all zeros, and this over here is all zeros as well. So it's all zeros except for the diagonal and then that one sub-diagonal column there. So for example, from what we just did up above, our L1 would be this. We had M2, 1 here, M3, 1 here, and a 0. So what were our multipliers? 4 and 7. It's right above me. Okay. So I'm claiming that this is the matrix that would essentially encode and accomplish those row operations. So now let's look at the properties of this K matrix. Would you believe that the inverse, you can invert that matrix just by negating that those sub-diagonal multipliers? You don't have to believe me because I'm going to prove it to you. So the inverse of that matrix LK up there is the same matrix except we put a minus sign in front of all these multipliers. Negative mk plus 1k all the way down to negative mnk. Now let's prove that. We'll prove it by multiplying, looking at what the result of multiplying L by some vector x looks like, then we'll just invert those equations. So here we have y equals that L sub k times any vector x. So what does the result look like? It looks like a vector y, any vector y. Now above the kth row, or even down to the kth row, it's just the identity matrix. So it's just copying the x value into the y value. Below, though, there's a mix. So let me just choose an example here. Negative m I k. So over here, we have a 1 in the ith column, because this is the ith row. So for all those rows, the resulting y value is a combination of xk, in fact it's that multiplier times xk, plus the ith x. So anyway, you should be able to convince yourself that this equation makes sense. And once you do that, let's invert it. Well, the first bunch are easy to invert. The xi is just equals the yi for I equals 1 to k. Now inverting the other ones, if I want to solve the second equation for xi, it's pretty easy. Because I can, sorry, if I want to solve it for xk, no, I want to solve it for xi. I want to solve it for xi. But I already know what xk is. It's just yk. So xi is really just taking this part and putting it to the other side. So yi minus mik yk. This is for I equals k plus 1 up to n, the size of the matrix. Okay, it was a bit messy, but I hope you followed it. Okay, so it's easy to invert these matrices, and we will use that inverse later on. Another interesting thing about these Gaussian matrices, Gaussian transformation matrices, is that their products are easy. At least some of their products are easy. So in particular, if you're multiplying two of them so that the one on the left has the subdiagonal, let me see here, the subdiagonal on the left, then they multiply nicely. So let me demonstrate it down here first. I'm looking at these two matrices here. So you can see we have the first, this is basically L1, and this is L2. So if we multiply those out, in this upper corner here, we have a 1, and that's not very interesting up here. Now let's look at this element here. It's a times 1, so we get the a copied there. And even below it, it's the same deal, b. Okay, what about this diagonal part here? It's not a 0, it's a 1. In fact, let me just copy those things out. So this C1, what's going to go down here? Is that going to be the C? Yes, it is. Let's see why. It's b times 0 plus 0 times 1 plus c times 1. So this is just a demonstration. It's not a proof. It's just a demonstration of the idea that multiplying these Gaussian transformation matrices is really easy. You just copy these subdiagonal columns. This only works in this order where the L matrix to the left of this product has a lower index, was part of, it came earlier in the Gaussian elimination process. Okay, so in that case, the product of those matrices is really just, you just copy those two subdiagonal columns. So it'd be mk plus 1k all the way down to mnk And then in this other column, the Lth column, M, L plus 1, L, down to M, N, L. So there could be zeros in between there, right? And there are zeros over here, there are zeros down here, and there are zeros in the superdiagonal, in the upper triangular part. Okay. So inverting those Gaussian transformation matrices is easy. Multiplying them is easy. So let's go back to the previous example and look at the first stage. So what we're looking at here is the first stage of Gaussian elimination. So from that, we can get L inverse, L1 inverse is, well, you just copy these ones, and you negate these multipliers. So it'd be -4 here, -7 here. Or if you like, I could have written, maybe I'll just do that. -M21 here, -M31 here. You can see what those values are there. So since A was, A primed, now I guess if you look at this matrix, at the way these linear operations were applied, this matrix A equals L1 inverse times A primed. No, it's the opposite. Applying that, oops, I did it again. Applying these linear operations to A gives us A primed. Okay, and so likewise, we can continue on. A double primed is equal to applying the inverse of L2 to A primed, which is the same as inverse of L2 times the inverse of L1 times the original A. So this A double primed is upper triangular, which we already saw, and I'll write it like that. So the U equals L2 inverse, L1 inverse times A. Okay, so from that you can infer that A equals, if I want to solve this equation for A, I peel the onion. I multiply left side both by L1, L2 and then L1. So whoa, turns into L1 times L2 times U. Right, that's just inverting it one layer, one matrix at a time. So by that rationale, putting together all the things we have up above, the fact that, so this L thing here, that's our L matrix. And we already learned that you can invert these L matrices by negating the subdiagonal parts, like these minus signs here. And then you can multiply them together by just copying them because they're in the right order. L1 comes before L2. So by that rationale, I can decompose the original matrix that I did as an example into the upper triangular part, which is here, 1, 2, 3, 0, -3, -6, 0, 0, -8. And the upper triangular part is just this identity matrix with the multipliers copied down below. Now notice it's the positive values. So these multipliers, as I had them up here, were 4 and 7, looking there. We added the minus signs implicitly into our row operations. Those minus signs were, anyway, you can track it, but we don't need those minus signs in this L matrix. It's just the multipliers themselves. Okay, hence, LU decomposition factors a matrix A into L and U, where U is upper triangular, and L is unit diagonal lower triangular. Okay, so this is LU decomposition or LU factorization, and it's equivalent to Gaussian elimination. Gaussian elimination is basically just a one-off way of doing it. If you record all those row operations in your L and U matrix, then it's LU factorization. Okay, so let's if we're going to turn this into an algorithm, so let's kind of redo this LU factorization and kind of looking more carefully at the different steps that we took and how we would implement it into code. Okay, so first thing we're doing is we have a loop where we're choosing a pivot element. So first we're going to choose this element up here as a pivot element, and then the stage following that we'll choose this as a pivot element, and then we'll be done. So that pivot variable I'm going to call looping over k. So k is going to be like the a sub kk will be our pivot element. So we're going to start out with the pivot at k equals 0. So when we do that, we just copy our first row, 1, 2, 3. Now, we know we're going to have zeros here, so we can just copy those. But it's this matrix down here that we have to focus on now in this phase of Gaussian elimination or LU factorization. So, pivot k. So I guess I flipped through the original. This is now pivot k equals 0. Okay, so what I'm showing here is the result of what happened after we had the pivot at k0 and we went through all the row operations. Okay, so we had a -3 here, -6 here, -6. What? Should that be -8? No, -6, -20. So this is after one row operation. So I skipped along here because in order to get these, right, okay, that's what I did. In order to get all the entries in that block underneath, we had to go down these rows, and I'm going to index those with L. So at each pivot stage, for each value of k, we have to go down the rows. Now for each row, we have to go across the columns to update all the values in each of those rows. So this is what I'm laying out here is a triple nested loop that composes LU factorization. So that was the k equals 0 when the pivot was at 0. When the pivot's at k equals 1, we get this new matrix, 1, 2, 3, and we've already taken care of the second row. And we get a -8 down here. And this is our U matrix. So as we're doing these, as we're going through these different stages of Gaussian elimination, though, we are recording these multipliers. So at this first stage of Gaussian elimination, as we're looking at the rows underneath the pivot element, we're recording the multipliers that we use. So we had a 4/1, and that got us our second row. And then we had a 7/1, which gave us our third row. Then for the next stage, to go over to k equals 1, this -3 was our pivot element. And so the multiplier we got was -6/-3, which is 2. So we record that in our L matrix as well. So I guess I don't have to rewrite it. So here we have our U and our L from Gaussian elimination. We went through the operations of Gaussian elimination to get an upper triangular U, and as we did, we recorded the multipliers in our matrix L. That's LU factorization. Okay, now that we've sort of gone through that more carefully, let's look at, well, this is actually very MATLAB-y, this code, but it's okay. So let's look at an implementation of LU factorization. So given a matrix A, let's assume for now that it's non-singular. In fact, I will introduce other factors later on, or other things that we'll need later on. But for now, let's just assume everything's going to work out nicely. So first thing I'm going to do is record, I'm in this algorithm, I'm going to ask how many rows there are. N equals number of rows in A. So that tells me how much I have to loop over. A will be an n by n matrix. I'm going to say L is the identity matrix n by n. And I'm going to add those multipliers in as I go. And U is going to be my original A. We're going to change U as we go. So this outer loop is over the pivot elements. We have to go, excuse me, k equals 0 to n minus 2. Right. So I guess this is not MATLAB-y in the sense that I'm using base 0 indexing. So the rows are indexed 0 to n minus 1. Is that what I do later on? Let me see here. Yeah, that's what I'm doing. Okay. So this is indexing base 0. Okay. So if the rows are indexed 0 to n minus 1, we only have to go through phases of Gaussian elimination up to, but not including the last row. So it only needs to go to n minus 2. Right? We didn't need to do anything in the last stage of Gaussian elimination because our last row is already what we want it to be. Okay, so that's the outer loop. Now inside that we need to go down the rows below the diagonal. So L is going to go from k plus 1 to n minus 1, the last row. So now for each of those rows, we're going to do row operations. We're going to replace row L with a linear combination of row L and row K. Because inside this K loop, we're basically looking at pivot element index KK. Okay, so the multiplier M is U KL I think I want the other way around. Should be LK. Row L, column K, divided by UKK, the element on the diagonal. I think my notes are wrong there. Row L, yeah. And I'm going to go ahead and set, I know that by design, the elements underneath in that subdiagonal below the pivot element are all going to be 0, so I'm just going to go ahead and set them. I'm not even going to compute them. It's just more work. LK is going to be 0. Okay, now for each of those rows, I have to actually, this last inner loop implements the row operation, so it does the linear combination of the rows. So column C is going to go from k plus 1 to n minus 1. We don't have to do anything with column K because we know it's just all zeros, but to the right of that. So U, row L, column C, is ULC, replacing row L with row L minus the multiplier times the corresponding element in the kth row. Okay, and after that, so that updates our U, we need to record that multiplier in our L matrix. So L, LK equals the multiplier. So this will do LU factorization. So we're going to come back to this in a bit, but for now, let's talk about sort of ways that make the implementation a little more clean and efficient. So one thing you can do is you can store U in A. So I made a copy of A and called it U, and so the original A is still sitting there. Really, what they often do is they do an in-place LU factorization. So you give it a matrix A, and it just goes ahead and rewrites it, and it changes it into U. So I could have replaced all of my references to U in this algorithm with A, as long as I don't mind the fact or make it clear that I'm doing an in-place LU factorization and changing the original A matrix. Excuse me. Here's another interesting thing. You can actually store the elements, the multipliers, in the same matrix. So you see up here, all the elements where the multipliers are, they're all equal to 0 in U. So you can actually store L and U in the same matrix. You don't need the diagonal of L because it's all just ones. You know it's all ones. So you can actually store L and U in the same matrix. In fact, you can, again, if you're willing to overwrite the original matrix A and do it in place, you can just take a matrix A in and spit out a matrix the same size that has U and L embedded in it. And finally, the innermost loop can be vectorized. So here's just an example of the inner loop performing the row operation. In Python and MATLAB and lots of languages, you can actually write it as something more like U row L, all of the columns, this is Python, equals, or I could even say plus equals, well, I'll just be a little bit simpler. U row L, all the columns, minus scalar multiplier times U row K, all the columns. Okay, actually what I really want, let me reformulate that a bit. I want it from C on to the end. Otherwise it's going to do adding and subtracting a bunch of zeros. That's not helpful. Not C, it is K plus 1 to the end. It's not, these details don't really matter. My point is that you can often do that innermost loop in a single line of code. It's still doing the same number of flops, but often different languages can implement these type of vector operations more quickly than it can execute the loop. So it's often more efficient to vectorize it like that. Okay, but let's look at the computational complexity. Oh, let's first do a joke. Okay, today's joke. My wife is blaming me for ruining her birthday. It's ridiculous. I didn't even realize it was her birthday. Okay, the computational complexity. So we're going to need some of these fancy schmancy summation finite sums. So I'm just going to lay them out ahead of time, that we can draw on them as we need them. So first of all, the sum of 1s, where k goes from 1 to n minus 1, is just n minus 1. Right? We're adding up 1 that many times. This sum of k, where k goes from 1 to n minus 1, equals 1/2 n times n minus 1. And according to my notes, this sum of k squared is 1/6 n times n minus 1 times 2n minus 1. Okay. So we'll use those in deriving the computational complexity of that LU factorization algorithm I just listed up above. Let's start with the innermost loop. So what I have here in this innermost loop, I have one multiplication and one addition. It's a subtraction, but it's addition. So I'll say there's one mult and one add. So 2 flops, if you like. Now this loop is done n minus k minus 1 times. It goes from the way, well, you can work at your own method. The way I do it is k plus 1 up to n minus 1. The way I do it is if you're adding for these, you subtract from n minus 1 the thing before where your list started. So it's n minus k minus 1. That may or may not make sense to you. You're an adult and a very intelligent person. You can work out yourself, prove it to yourself that n minus k minus 1 is the right answer. Okay. So if that's the case, then the computational complexity of that inner loop, which I'll call WC, is the sum, c equals k plus 1 to n minus 1, of 2 flops inside. So it's 2 times, and we just established that's n minus k minus 1 iterations or executions of that inner loop, or the stuff inside that innermost loop. Okay, the W loop. So the W loop is the next one out. Why did I call it W loop? K loop, sorry. No, L loop. L loop, this is going down the rows now. So inside that loop, we do the W's, we do this whole C loop in here, so we'll include that. But we're also doing one more multiplication. Okay, now in this loop, we're executing how many times? Again, it's n minus k minus 1. Okay. All right, so this loop is going for L equals k plus 1 to n minus 1 of WC plus 1. That 1 is that extra multiplication that we're doing. It's actually division to get that multiplier. Okay, so I can rewrite this. Come on, if I can erase it. I'll put the 1 out in front because I can pull it out. Oh yeah, this is actually constant. That 1 plus WC for any given L is constant. So it's basically n minus k minus 1 things we're adding up. And the things that we're adding up are 1 plus 2 times n minus k minus 1. That's WK, or WC, I mean. And it's equal to n minus k minus 1 plus 2 times n minus k minus 1 squared. Okay, that's WL. Now that we're doing inside each of our K loops. So our K loop out here, excuse me, is way out here. So we're doing this n minus 1, n minus 2 times. I have n minus 1. Oh, right, n minus 2 minus negative 1. Yes. Okay. That works. Okay. Okay. So we're adding up for k equals 0 to n minus 2 WL, which is, I'll just plug in that formula we have above. N minus k minus 1 plus 2 n minus k minus 1 squared. So first of all, I'm going to look at this thing and say, what am I going to get out of that? It's going to be order n squared. So that's going to appear down below, but I'm not going to explicitly evaluate it. So that this other quadratic term is going to be the one that sort of dictates the order of our method. Okay. So that first thing is going to be a bit messy, but let's simplify it. I'm going to do change of variables. So I think this is an eta. Let eta equal n minus k minus 1. So I'm going to rewrite the formula using eta instead. To do that, I'll need to replace k. So when k equals 0, that's the where my loop starts, my sum starts. That gives me eta value of n minus 1. Right, just looking directly at this formula, when I set k equals 0 in there, I get n minus 1. The other end of the loop, or sum, k equals n minus 2, that gives me an eta value of n minus 2 minus 1. I believe it's a 1. n minus 2, yes. So this new sum actually goes eta equals 1 to n minus 1, replacing those k values with the corresponding eta values. I did flip it upside down, but it's okay. We're just adding the same terms in the opposite order. That's okay. Eta squared plus order n squared from before. So eta squared, sum from 1 to n minus 1 is, there's the 2 from before, 1/6 times n minus 1, 2n minus 1 plus order n squared. So looking at the leading term, it's going to be 2 over 6. So it's 1. Right, the leading term is going to come from this n, and that 2n. So that 2 is going to cancel with that 2, if you like. And I'm going to be left with, sorry, that they're not going to cancel, they're going to multiply. Whoops. So I'm going to get 4 over 6, or 2/3 n cubed plus order n squared. Everything else I'll just tuck into the n squared. Okay, so therefore the cost of LU decomposition is 2/3 n cubed plus order n squared, where our matrix that we're starting out with is n by n. Floating point operations. Okay, how do we use the LU factorization to solve the system that we started out with in the first place? We have to, I promised you that when you form that augmented matrix and you do the row operations and you do the row operations on the B side at the same time, you would take that, at least the way I learned it, you'd then solve that augmented system. So how do we do it with LU factorization? I promised you that the stuff that you're doing to B in that augmented system are actually recorded in L. So here's how you solve AX equals B. First thing you do is you get A equals LU. You do the LU factorization, make it look more like a U, less like a V. A equals LU. So you do the LU factorization. That's order n cubed. It's a lot of work, relatively speaking. Then phase 2, you use that LU factorization to solve the system. So what our new system, instead of being AX equals B, it's LUX equals b. Okay, so how do you solve that? Well, we have simple ways of solving triangular systems, and I won't go into detail, but they're called forward substitution and backward substitution. And they're order n squared, so they're actually cheaper than the LU factorization itself. So I'll demonstrate the forward substitution and backward substitution in a minute. But what we do is we call this LU times x thing, give it a different name. We'll call it y. So then what we need to do is solve Ly equals b for y. And this is done with forward substitution. Substitution, I don't like that b. Forward substitution, I'll demonstrate in a second. And then once we've got that y, then we solve ux equals y, because we defined y as equal to u times x. And then we solve that using backward substitution. Substitution, yes. Okay, so it's a two-step process. You peel off the L first, and then you peel off the U, using forward and then backward substitution. So what does forward substitution look like? Let me solve this system here. It's unit diagonal upper triangular, which is what LU will give us. So we start with the first row. It's easy because it's basically the first equation, the first row basically is just y1 equals 1. That's easy. So we get 1. Now the second row, now we know what y1 is. The second row can be written as 4y1 plus y2 equals 1. But we already know what y1 is, so we can move that 4y1 to the other side and solve directly for y2. So that's why what we get is 1 minus 4 times y1, which was 1. So that's negative 3. Same deal with this last equation. We already know what y1 and y2 are, so we can solve for y3 explicitly. So it'll be 1 minus 7 times y1 minus negative 3 minus 2 times negative 3. I'll write it like that. And I believe that's a 0. So that's a demonstration of forward substitution. Very easy to implement on a computer, obviously. Backward substitution. So back substitution is the same deal, except you start with the last row because it has only one element. So if I'm doing the LU factorization, I take my y vector and it goes here, because this was solving Ly equals b. Now this is solving ux equals y. So I start with the last one. The x3 equals 0, so that's easy, 0. Negative 8 times x3 was 0, so that happens to be easier than normal. The next equation up, let me write it out. Negative 3x2 minus 6x3 equals negative 3. So if I want to, I already know what x3 is, so to solve that for x2, it's equal to negative 3 minus 6x3. And then I divide both sides by the negative 3 here. Okay, so that just gives you a bit of insight into where I'm getting this next thing. It's negative 3 minus 6 times x3, which was 0, all over negative 3, which is 1. And the same deal with the x1. I already know what x2 and x3 are, so I can solve for x1 explicitly. It is it's 1 minus 1 times, minus 2 times x2, which is 1, minus 3 times x3, which is 0, all of which is over 1 in this case. It's this multiplier for x1. And that evaluates to negative 1. And you can check it. Here's the original A matrix, and I can multiply by what I'm claiming is the solution, and I should get 1, 1, 1, which was way, wow, that far back? Oh. Did I ever tell you what the right, oh, it's, well, here's the right-hand side, the B. Okay. So just to be more explicit about it, let me actually write out the algorithm for forward substitution. Given a lower triangular matrix L, lower triangular unit diagonal matrix L, and the right-hand side vector B, the forward substitution, again, we figure out how many rows we have. Now, why? I'm going to start with B, and the reason for that is because you just copy B in, and then you're basically going to be subtracting stuff off. But you're going to subtract them off in the order of starting with from low index higher and higher. Yeah, so for K is going to go down. Right, okay. So K is going to visit all the elements from 1 to n minus 1. Oops. We don't need to visit element 0 because we already copied it over into y. Y sub 0. Yeah, great. I'm using index base 1 up here, and for these x's. Now down here I'm using index base 0. So sorry about that, but you know, you're professionals. You can handle this. Again, this is index base 0. So we don't need to worry y0 will equal b0. That part's already done. So we only have to visit y1 and higher. So for each y beyond that, the C, now the C loop is going to count through the variables that we've already solved for and subtract those off. So it's going to go from 0 to k minus 1, because we're right now working on the kth one. And then y sub k will equal itself minus lkc times yc. Okay, subtracting off those bits for the values that we've already computed, because we already know those c values from 0 to k minus 1. Okay, we're going to do a computational complexity analysis of this. So I point out here that there are k loops, there are k executions of that loop. And I guess I point out that there are 2 flops in that loop. There's a multiplication and an add in that loop. So that C loop is, the whole C loop is 2 times k flops. Okay, to implement the whole C loop, not just what's inside the C loop, but the whole C loop itself. And then the WK, the outer loop, is the sum for k equals 1 to n minus 1 of WC, which is 2 times this sum, k equals 1 to n minus 1 of k, which is 2 times 1/2 n times n minus 1 from those formulas I had up above. So this is n squared plus order n flops. Okay, so remember LU factorization was n, it was 2/3 n cubed. That's more expensive because as n gets bigger, as we double the size of our matrix, we multiply the amount of work we have to do by 8. Whereas for forward substitution, if you double the size, you only multiply the amount of work you have to do by 4. That's cheaper. Backward substitution is also n squared plus order n flops. Right, yes. There is an extra division that we have to do for the back substitution, dividing by the diagonal element, but that gets soaked up in this order n. It's only done n times, or n minus 1 times. N times. Okay. Pivoting. So before I said A equals LU, except, A has to be non-singular, has to be invertible. I guess you can factor it even if it's singular. Fine, whatever. It won't be very helpful. You can get the rank of it. Anyway, if you actually want to solve the system using LU, you can run into trouble. So let me show you where LU can run into trouble, even if A is non-singular. So let me give you this system. 0, 1, 1, 2 equals 1, 0. Okay, so we look at this and we go, okay, Gaussian elimination, great. Here's our pivot element. Our multiplier is the 1 over 0, and then, oh, wait a second. We can't have 1 over 0 as a multiplier. That's undefined. So our Gaussian elimination breaks down immediately. But these are just two equations. The fact that they're written as x1 equals 1 and x1 plus 2x2 equals 0 in that order, I could have written them in the opposite order. I could have written this one first. Whoops. Whoops, come on. Right, now that is an equivalent system. The matrix is different, but it has the same solution. So let's do that. Let's just swap those rows. So swapping rows 1 and 2, I get a different system that looks like this. Now this can be LU factorized. In fact, it's already LU factorized. For some reason I have Cx equals D. So C is different from the original A. D is different from the original B. But I can compute the LU factorization of C. So A and C are related by a permutation matrix, which we call P. In this case, it's 0, 1, 1, 0. So permutation matrix times A equals C. So therefore, permutation of A equals LU. Right? If C equals LU and a permutation of A equals C, then A equals LU. So there are times when you need to swap rows in order to make your pivot element non-zero. But it's a little bit more useful than that, which I'll describe in a minute. Okay, P is a permutation matrix. Let's talk about these permutation matrices. A permutation matrix is any matrix, a square matrix, where it's all zeros except there's 1, 1 in each row and in each column. So basically, well, I'm showing an example here. This 3 by 3 matrix is a permutation matrix. If you left multiply, it permutes rows. Incidentally, if you right multiply by so for example, for left multiplication, left multiplying, that will permute the rows of A, permute the rows of A. If you left multiply, it permutes the columns. Okay, so we're only going to talk about row swapping, permuting rows. But you should keep in mind that you can also permute columns. It's basically, permuting columns is just like reordering the orders of the terms in this system. I could swap these things as well. Yeah, okay. We're only going to focus on row swapping. There's this nice property. Every permutation matrix has a determinant of plus or minus 1. So in fact, interchanging two rows of a matrix changes the sign of the determinant. So if the permutation matrix has one row swap, the determinant's minus 1. If you have two row swaps, the determinant's plus 1 again. Okay. P is an elementary permutation matrix if and only if P can be obtained from the identity matrix by interchanging two rows. So there's general permutation matrices which can reorder all the rows in whatever, shuffle them into whatever order you want. An elementary permutation matrix is swapping only two rows. Okay, so let PRS be the elementary permutation matrix that swaps rows R and S. So these are some neat properties. If this permutation matrix swaps rows R and S, then you can undo it by just swapping rows R and S again. So an elementary permutation matrix is its own inverse, which is kind of cool. I can go like this, and then go like this. Forward, inverse, forward, inverse. Not only that, but because these are orthogonal matrices, the inverse is also the transpose. Any permutation matrix can be written as a product of elementary permutation matrices. So if you want to swap a whole bunch of rows, you can implement that by swapping two rows at a time in sequence. So any permutation matrix can be written down or represented as a product of elementary row operations, elementary permutation matrices. And finally, because of the things up above, P transpose times P equals the identity matrix, which is because P inverse is P transpose, it's an orthogonal matrix. Although I justified number 2 by claiming it's an orthogonal matrix, so that's circular logic. So how do I get out of that? Well, circular logic works because circular logic works because circular logic works because circular. You get it? I think statement 1 is enough. If it's its own inverse, I'm not sure. I'm not sure how to prove 2. I doubt it's very difficult. I just can't think off the top of my head how to do it. I guess if a matrix is its own inverse, it's orthogonal, and an orthogonal matrix is inverted by transposing it. Okay, let's move on anyway. Theorem. So this is the LU factorization theorem. This is what you've all been waiting for. Every non-singular matrix A can be factored as PA equals LU, where P is a permutation matrix, L is a unit diagonal lower triangular matrix, and U is an upper triangular matrix and is non-singular. If A, just for the sake of addressing my comment before, what if A is singular? I think you could still do this factorization, but the U that you get will be singular as well. But you can still get a U matrix. Okay, but for this theorem, we're going to assume that A is non-singular, which means it's invertible. We're going to show that we can decompose it into PA equals LU. We can decompose PA into a lower triangular unit diagonal and an upper triangular matrix. We're going to prove this by induction. So how do you prove by induction? You start with a base case, and prove it's true. We're going to prove it true for n equals 1, 1 by 1 matrix. Then we're going to assume it's true for some later n, and then show that if it's true for n, it must also be true for n plus 1 matrix of size. If we assume it's true for a matrix of size n, we show it's true for a matrix for size n plus 1. Okay, base case is when n equals 1. Well, this is just the scalar case. 1 times a equals 1 times a. So for scalar, it's already upper triangular, and multiplying by 1, that's lower triangular unit diagonal. Okay, so it works for n equals 1. So we're going to assume it's true for n bigger than 1. So if it is, then we know that we can write down, now this superscript n in brackets means for matrix of size n by n. Because pretty soon we're going to be talking about matrices of size n plus 1 by n plus 1. So we know we can do this for all non-singular okay. I guess I should do n. Now we're going to show it's true for big N equals little n plus 1. Okay, since A is non-singular, there exists an element in the ith row. There exists, it's written right here, there exists a non-zero element in the first column of A. Okay, we look down row i's, I going from 0 to big N, and we can find, if the column was all zeros, then it's a singular matrix. So we can find a non-zero element in the first column. What we're going to do is swap, it doesn't matter which one, but choose one of the rows that has a non-zero element in the first row, first column, swap that up into the first row. So let P1 superscript n be the permutation matrix that swaps row 1 and row I. Okay, so now we know we have a non-zero pivot element. So let's construct our L this way. I'm going to construct these blockwise. So I'm sort of cordoning off here, fencing off the first row. I'm going to put a 1 here, and then a row of zeros. I'm going to put here a vector m. Let me rewrite that. A vector m, and here's going to be an identity matrix. So that identity matrix is little n by little n, and this big L matrix is big N by big N. It's one bigger. So m is going to be these multipliers I would use, m21 down to mn1, where m k1 equals okay, just the multipliers. Guess I could have used I instead of K to be consistent with what I had up here. It doesn't really matter. So that's basically the L matrix that we would generate as we're doing LU factorization. So because of that, we can write L1n that we just constructed times our matrix that we start out with is equal to our original A, permuted version of our original A. Right, so that if you're not sure about that, you can look up above where I derived the LU factorization algorithm. So now this AN will be what we get from after the first phase of Gaussian elimination. So again, describing it blockwise, we'll have some U11 element up here. It's actually just, it'll be A11. We'll have some vector here, U1 transpose, I'll call it. We'll have zeros down here, which is the whole purpose of doing Gaussian elimination. And down here, we'll have a matrix that's not big N by big N, but little n by little n, one smaller in each dimension. And I'm calling it A sub 2 there. Now we know, because our pivot element was non-zero, that top left corner is non-zero. I've changed to U for some reason. I guess AU doesn't really matter. And that U1 transpose is U12 so it's just copying the rows from that A matrix. Just like you do in Gaussian elimination, you copy whatever pivot row you're working on, you just copy that row. Okay. This seems like a good place to stop. We've been going for quite a while now. Tune in next lecture, where I will finish this proof and we'll continue talking about LU factorization.